I've got a hard act to follow, but I'll try and do my best. I'm going to take you through a bit about the definitions of the Anthropocene from a geological point of view. I won't spend too much time on that because we had a really good talk by Jan about that yesterday. I'll then take you through a bit more about big time, about deep geological time, and what lessons there might be in that for us in what we're facing right now. And then I'll finally consider what sort of record in the geological sense that our civilization will leave. What will it look like from a point of view tens of millions of years in the future? So you've seen this yesterday, a chart, and this is the most recent one, the 2015 edition. You can go to this website and download these every year because they do change from time to time. We're not, at the moment, so interested in the older bit, but we do need to talk about this more recent section, which currently just has the Holocene. Now, these are in millions of years, which we abbreviate with a capital MA. And you'll see also that on these diagrams, there are these little golden spikes. And these are the strata types that are used to define these boundaries. And you'll see that in this most recent one, the Anthropocene doesn't exist so far. So it's a fairly new concept, and it's only been defined for 15 years or so. So how might it go in terms of being defined? Well, Lewis and Maslin, in a paper in Nature this year, suggested potentially it could be an epoch, either following a Holocenian stage or following the Holocene epoch. And there's a question mark in their paper about exactly when that transition might be, and I'll just spend a few slides looking at that. We see the influence of humans potentially with the megafaunal extinctions, which happened up to 50,000 years ago. But then we move into the Neolithic period where we see evidence for human agriculture and forest clearing, and then moving through into the industrial era, and we've been hearing plenty about that. So there could be an early Anthropocene proposal, and potentially we could actually redefine the whole Holocene as the Anthropocene, as Ruderman has suggested. My colleague Steve Foley in Macquarie University wrote this quite interesting paper about potentially the Palaeoanthropocene, taking the place of the earlier part and then leaving it until the Industrial Revolution around about 1950 or so to actually have the Anthropocene coming in with increasing global change as represented on this graph. Now, a couple of things about this graph. Firstly, it's a log scale along time, and also the time is the other way around. Now, I much prefer going to the right, and most of the time diagrams we've seen at this conference have gone to the right, so I'll just flip this diagram around like this, and that will fix that one. Okay, we've heard quite a bit about this, so either the Industrial Revolution might be a good starting point, either from 16s or 1700s, with this takeoff, the Great Acceleration, or potentially the great nuclear bomb explosions might provide a means of getting a strata type, because that is a strong isotopic signal that's preserved in rocks and means we could actually define a boundary a bit easier. Okay, so just to summarize that, different periods to potentially say when we change into it. But it's been pointed out by Monot-Skursky that maybe we will have to leave it until much more into the future to really decide when it actually started, to see what really lasting impact humans had on the planet. In fact, I actually believe that, in fact, the idea of when the Anthropocene starts is not quite so important. What I'm actually a bit more interested in is when will it finish? And that's actually a very pertinent question. So what I'd like to do is then think about how some of these timeframes compare to previous large biotic events that have affected the Earth. So this is where I dive back into deeper time. So this is a bit more like the big history approach. We've got 4.5 billion years of Earth history shown on this diagram from when the Earth formed. There's evidence for early evolution of life from light carbon isotopes 3.8 billion years ago. And then More definitely, by 3.5 billion years ago, we have definite evidence of life through microfossils, such as these guys, which look a bit like cyanobacteria, and these stromatolites, which are microbial mounds produced by cyanobacteria and other bacteria. And this was published by an ex-Macquarie University student, Abby Allwood. And there's a little story about that. She did a PhD here, and now she's the first woman and the first Australian to be leading a mission to Mars to go exploring for life. She's on the 2020 mission. So she's a great success story for Australia and for Macquarie University. Okay, so these stromatolites and the cyanobacteria were living here. And very interestingly, they actually had a very major effect on the Earth system. So humans are not actually the first species to cause a major biotic event. This is an oxygen curve showing that when life evolved on Earth, it was a very anaerobic system, meaning completely low oxygen. And there's a period called the Great Oxidation Event, which we briefly heard about yesterday, where oxygen levels did not increase to present day, but they went to about 7% or so, as estimated by various people. So this actually caused a very large effect on the biosphere. There was what's being called an oxygen holocaust, because all the anaerobes that were living would no longer have been able to survive on the surface of Earth. So in fact, these photosynthesizing bacteria were the guys who produced the oxygen. They were taking CO2 from the atmosphere, they were producing oxygen, and that slowly accumulated. And then eventually, it overcame all the reduced minerals and then started accumulating in the world's oceans and atmospheres, which are inextricably linked. So this period from when life evolved, around 3.5 or a bit earlier, to when this oxidation event happened, soon after, around 2.3 or 2.5, is a long period of time. So it's a real slow burn, that one. So now I'm going to move forward to about 0.5 billion years ago, the Ediacaran-Cambrian transition. This is a period where the first animals were starting to live on Earth, and shortly after another increase in the oxidation levels of Earth. So prior to this event, there were these Ediacaran fossils, or at least we see them as fossils. These were soft-bodied animals that crawled around the seabed or were attached using holdfasts. And then fairly soon after that, they were superseded by these Cambrian animals, the things with teeth, like Anomalocaris on the board here. So this was a major biotic revolution. And it's been proposed, in fact, by Darroch in a paper this year, that this is actually a major mass extinction. It hasn't been thought of so much as a mass extinction so far. But it was one driven by biology. It was ecological innovation, ecosystem engineering, and in particular the development of those predator-prey interactions. The time it took for that to happen was something in the order of several million years. So again, a very slow process. Okay, so that brings me to talk about some of the mass extinctions through the later period of Earth time, the more recent stuff, which is only 500 million years long. So this little graph shows quite simply major times in Earth's history where there have been big drops in proportions of biota. And we define mass extinctions where these drops happen of more than 75% of the biota. And these happened at the end Ordovician, end Devonian, end Permian, end Triassic, and end Cretaceous. So potentially we're actually in number 6 now, and I'll say a bit more about that in a second. So the past, the geological past, is the key to understanding the present and future of Earth. So we can look at the extinction rate, and you'll notice, in fact, that extinctions don't just happen in mass extinctions, they're going on all the time of life. Then we move into the last 60 million years, a bit closer to present, in this middle panel of this diagram. And we start tracking extinction rates of organisms and getting an idea of what's happening. And then we can start looking at historical time and seeing the tracking of different species and how many are going extinct. So we can start forming a view about what's been happening. But before we look at the present, let's just look at a couple of the events in the past. So let's start with the end Permian. So the Permian was a very nicely oxic environment. There was bioturbation. There were lots of these organisms living both in the sediment and in the water column. And when we transferred or translated into the Triassic, it became a strongly anoxic system. There's lots of pyrite, which is an iron sulfide mineral. And the ecosystem completely changed, and it changed really very quickly. Now, why did this big mass extinction happen, the biggest of them all? Well, very likely it was partly caused, at least, by massive volcanism. Incidentally, the processes or the causes of these mass extinctions are commonly still quite controversial, still debated, but there are some common themes. And volcanism seems to be a common theme. So massive volcanism produces a lot of CO2, a lot of methane. So that's not perhaps so different to what we're seeing today, but from a different cause. It's likely this caused global warming. There was definitely oceanic anoxia, which means there was less circulation of currents and that the oceans became stratified. There was high amounts of hydrogen sulfide in the oceans and therefore into the sediments. And the warming up of the oceans caused very likely melting of methane hydrates, which are preserved in ocean sediments. And this puts us into a positive feedback system, and in fact the Earth experienced something like 6 degrees warming. And that amount of warming was enough to cause loss of something like 96% of the species on the big species on Earth, not counting the microbial communities. So how long did this happen? Well, something in the order of 160,000 years to 2.8 million years. And the recovery took something like 10 million years. So you'll notice that these numbers are massive. They're very long periods, and that's something that non-geologists always have a much more harder time to really grasp. Okay, so the other one I want to say a bit about is the end Cretaceous extinction, where potentially the large meteorite has had a role. You can see the data on the biota in the green bars showing the sudden stop of much fauna and flora and big geochemical changes. At the same time, or just preceding this large meteorite fall, there was a lot of volcanism again. The Deccan traps in the Indian area were being formed, and this may well have started some global warming before the meteorite impact. So the ecosystem, the biosphere, was probably under stress already, but by the time that meteorite arrived in Mexico. The meteorite impact certainly caused catastrophic environmental effects. We can trace it with an iridium anomaly around the world. It caused extended darkness, global cooling and acid rain, and there was loss of about 76% of the species. Now, if you believe it was all down to the meteorite, that's less than a year impact. But if you think that the Deccan traps were actually the major thing causing it, then it's a much longer burn for this event as well. Now, we've heard a little bit about the Palaeocene Eocene thermal maxima, and I'll say a little bit more just now. This was an event that occurred not as a mass extinction, but it caused a big carbon isotope excursion. So the carbon isotopes went from something around minus 24 for the dinoflagellate carbon down to about minus 28. So it became a very light carbon isotope system. And interestingly, we see influences in the sedimentary record quite a bit earlier than this. So there was changes in the dinoflagellates, which are these little calcium carbonate secreted microorganisms, something like 40 centimeters deeper in the sediment, which is about equivalent to 4,000 to 5,000 years. So these little dinoflagellates are picking up a change before this big input of light carbon. And then secondly, we can actually measure temperature or paleotemperature using proxies like this. This is called TEX86, which is a paleotemperature parameter which is measured in an organic geochemical lab such as mine. And this data shows the extent of the warming. So going from about 27 degree world up to about 34 degrees. Now, interestingly, that happened not at the same time as the dinoflagellate first changes, but still happened quite a bit before the isotope excursion. So half of the warming occurred prior. So why would that be? And incidentally, these time intervals and the depths are indicating sedimentation rate about 8 to 10 centimetres per year. So very likely what happened in this event was, again, massive volcanism. In this time, it was in East Greenland, and this would have caused global warming with a huge amount of light carbon being put into the ocean atmosphere system. Likely what happened was that warming water propagated down to the bottom of the oceans. And that would have taken quite a lot of time. So it takes a while to warm the oceans right the way through, and then eventually it would have warmed up some of the submarine methane hydrates, and then it's been modelled that you can get a -3 per mil isotope shift with an influx of methane from those hydrates of something like 2,000 gigatons. And there's a real lesson for us in that. We do not want that to happen to the current world. Incidentally, the timing of this is quite controversial. There was another paper I found whilst researching this talk about some of the rhythmic bedding in the Palaeocene Eocene sediments. And these dark bands you can see have been interpreted potentially as annual layers, in which case everything would have happened much, much quicker. That would imply a very high sedimentation rate of 2 centimetres per year and near instantaneous to decades methane release. I'm actually not so sure that really is a plausible mechanism, but it's still worth thinking about. Okay, so returning to the Earth's sixth mass extinction, we saw a different graphic from the Barnowski paper yesterday about this. And this is tracking some of the extinction events I've already shown and where we are now with the already extinct organisms, the critically endangered, and the threatened. And the bottom line from this paper is that if all the threatened species become extinct in the next 100 years or so, we will reach a 75%, which is a mass extinction, for the frogs or amphibians around 240 years' time, and for some birds, say 540. So this is only in the order of a few hundred years away that we could be facing a mass extinction. So let's just think about the geological record of humans from a viewpoint into the future, tens of million years in the future. And to do this, I'm going to employ a geologist of the future, because I don't think it will be a human. So this geologist has a geological hammer, because of course all geologists need a bed to break open rocks and have a look at the rocks. I've drawn on the time chart from 500 to present, and then a dotted line, because we don't know where the Anthropocene will end, and then perhaps a future geological period, which might be one of these rather warm periods. So which rocks will preserve the signal of what happened in the Anthropocene? Well, the igneous rocks, the ones that are produced from molten rocks, like these ones coming up through the volcanoes and in here, are from crystallization of magma, and they won't preserve our signal. And similarly, these deeply buried rocks, which get heated and metamorphosed, these will probably not preserve our signal. And what I'm saying here, in fact, is the big system of Earth, the recycling through plate tectonics, will probably continue unperturbed by anything that happens on the surface to do with humans. So we are not talking about saving the Earth will be just fine. It's actually saving the stuff in the biosphere we need to be worried about. Whoops, pardon me. So where we will see preservation of our signal is in the sedimentary rocks, and those are deposited from depositional material. So things like clays and organic matter is living in a water column, gets preserved into sediments, and that might be called a clay, and then when they get buried, it becomes a clay stone. It's more likely that the record will be preserved in aqueous rocks, such as marine and lacustrine ones. Of course, it's more useful if we can track what happened in the continental rocks, because that's where most humans live. So that might mean we need to look at lake sediments or shallow marine sediments. And in fact, these sedimentary rocks have very different preservation times. So fast sedimentation might be 25 centimetres per 1,000 years. And slow, such as the bottom of deep oceans, much, much slower than that. And of course, there might be more catastrophic type events where you have large sets of sediment being preserved, such as unusual sea slides. So let's have a look at what sort of sediments might be showing these sort of transitions. These are from the northern hemisphere, where you have glacial sediments, the pale ones at the bottom of these cores from lakes, being suddenly changing into very organic-rich deposits with these black sediments at the top, reflecting deglaciation in this part of these areas. And in fact, you can see this happening with a retreat of, in this case, the Geraldine Glacier from 1949 to 1993. It's affecting the lakes. They're going from vague turbid things to much clearer things. And we see the influence of that in the lakes, as in this case preserved by various microfossils. So we can track how the microfossils are changing, and also how things like carbon-nitrogen ratio are changing, which are reflecting the change in that particular environment. So what will the Anthropocene sedimentary rocks look like? Well, as I suspect, they'll probably record a mass extinction, sudden change in sedimentary characteristics due to that land use and runoff, and retreat of deltas due to dams, for example. And then a whole bunch of geochemical proxies, many of which we've heard about yesterday and earlier today, so I won't go all through those. I will note that plastics and microplastics are becoming very abundant in sediments. Those microplastics are really getting everywhere. Very interesting to look at. There's a whole bunch of anthropogenic chemicals, which are fairly novel, which will be a way of tracing our civilization. Now, some are short-lived, so things like the pesticide, like pentachlorophenol, that doesn't have much preservation potential. And the CFCs break down quite quickly in some anaerobic conditions, but others of these are really quite long-lived. So the PCBs, these diisopropyl naphthalenes, which I've worked on, lead from petrol, oil spill hydrocarbons, and some of these big aromatic compounds. These will be ways that our civilization is recorded in the sediments. And you can see this nowadays, for example, in the Clyde estuary. We've got profiles showing the polycyclic aromatic hydrocarbons increasing during this industrialization phase, and then obviously a big pulse of the PCBs from 65 to 77. So we can see the sorts of sediments being recorded right now and how they will look eventually preserved, or maybe preserved, into the geological future. So Jan also did this rather interesting paper in the journal Anthropocene, where he talked about the bioturbation by humans, which he called anthroturbation. And he pointed out that sediments and rock drilling, including nuclear testing, produce very long holes which will be visible deep into the geological future. And of course, mines and quarries will be as well, and various archaeological relics of our cities, the buildings, the pipes, and so on. So these have cross-cutting relationships, and no other species has ever done this before. And in fact, they will have long-term potential, because, say, a 4-kilometre borehole looking for oil, even if that's unroofed straight away and it comes up at maybe 2 millimetres per year, that gives a life for that rather funny cross-cutting relationship of 2 million years. So for several and many millions of years, there'll be information preserved in sedimentary rocks about humans' activities. Oops, pardon me. So just to summarise the talk, I've told you about some of the timing of the Anthropocene and referred to the Great Acceleration. I've shown you how past mass extinctions can inform us about the future, and understanding that rate of change is really the key, because that sedimentation rate means that discerning small time increments in the geological record is quite a rather tricky endeavour, and we need to get the timing right to really understand what happened when. I suspect that the Anthropocene sedimentary rocks will preserve our passing, especially through unusual contaminants and through environmental perturbations. And I guess the last thing I'll say is, I've talked about mass extinctions, and then probably some of you are thinking, well, will humans be part of that? I don't know. I think our civilization is in significant danger from everything that's been said, for example, earlier today. But it may be that humans, as a species, have a bit longer longevity than potentially our civilization. So just because a civilization collapses doesn't mean to say humans necessarily are extinct. Thanks for your attention. Happy to take any questions. Certainly there's a glaciostatic rebound. So when you have an ice sheet on a continent and you remove the ice, it will tend to push up a little bit. And potentially that could cause a phase of volcanism, but in fact, the main volcanism that we see and the ones that are connected with these big planetary cycles are completely independent of that sort of weather system. There are things that are happening on a much broader, longer-term scale in the Earth, caused by dynamics in the mantle, the deeper part of Earth. So I don't think there's a very quick connection there. It would be just coincidence if something like the Yellowstone volcano, a supervolcano, erupted. It wouldn't be very convenient for us, but it would be a complete coincidence if it happened right now. Well, I guess what I'll repeat is my answer to the previous question, which the major supervolcanic eruptions are really differently controlled. There's always volcanism going on, but there's no particular thought that that's going to increase right now. Well, I'll refer you to the Nature paper by Bonoski. So he's looked at the extinction rates and profiles of various different animal groups, and he's been trying to look at the rate of change of those different animal groups, and comparing that with those events in the past where the columns show the time variation. I didn't explain that because I didn't have enough time, but there's a big differences in time estimates for how long the extinction event happened. And then the intensity was to the right of that diagram. But it's a short paper and it's well worth a read. It's in Nature. So the isotopes I mainly talked about were the stable isotopes, the carbon-12 and carbon-13, which aren't influenced by the cosmic rays. So that influences the carbon-14 ratio, which is used for dating of things that are roughly about 50,000 years or less. So pretty good in the Holocene and through archaeology. And we've got a pretty good handle on the rate of that change. But it is not very useful, or not useful at all, for older things. So geologists working on rocks older than 50,000 years can't use that sort of the carbon-14 system for that.